Okay, we're going to continue on lecturing here. We got into chapter 14, I think, and chapter 14 obviously is about acid and bases, and we kind of opened up chapter 14, sort of talking about calculations of pH, POH, H plus, and again, a reminder, there's a couple of important formulas. We have our H plus and our OH minus from our KW, which is our 1 times 10 to minus 14. We also have our pH is minus the log of the H plus concentration. And a similar sort of calculation that measures OH minus is our POH minus the log of the OH minus concentration. And again, these two together will equal 14. We also saw, again, if you have the pH, you can get your H plus concentration from the inverse log of the minus pH. And same thing, if you have the POH, you can get the OH minus concentration as the inverse log of the minus POH. So as we talked about last time, again, there is sort of a variety of ways you can kind of get to these answers, depending on sort of the path you take, but they all really should get you the same answer as long as you choose a legitimate pathway. We also talked about towards the end there that if we don't have sort of a generic H plus or OH minus given to us, but if we do have a strong acid or strong base given to us, we essentially could get the H plus or OH minus from the acid or base. So once again, if you had something like hydrochloric acid, which is a strong acid, it will 100% break apart into H plus and Cl minus. And if you know the molarity of this guy, that should allow you to get to the molarity of the H plus and also calculate the pH in that particular case. You could also do the same thing for a strong base, like KOH, for example, K plus and OH minus. And once again, obviously, if you know that concentration could get you to there. We did come across one, though, that was not a one-to-one relationship, so you do have to keep that in mind. You might have to adjust the concentration. I think we did barium hydroxide maybe or something on that example, or calcium hydroxide, and it was a sort of 1-to-2 relationship between the base and the hydroxide. So you do want to make sure you adjust it if necessary. Also, if you are doing obviously a strong base, you will most likely be calculating the POH, and again, that is not the pH, so you do need to subtract the 14 there to get yourself to the pH. We talked about weak acids, which mainly stay together. So weak acids are really equilibrium type of situation. And because they mainly stay together, they will set up this equilibrium. And again, that is why they are considered a weak acid. They stay mainly together, but they still are able to produce some free H plus, and that then will make them an acid. They will not produce, obviously, anywhere near probably the amount of H plus a strong acid would produce. Because they could do an equilibrium, we could set up our favorite thing, which is an equilibrium constant for it, which is just like normal, our products divided by reactants. We also will do really a normal sort of equilibrium calculation involving weak acids by using an ice table. The one main difference is in most cases, we're interested in the pH. So when we get to sort of the equilibrium line, that is essentially what we're looking for, is really what the concentration of H plus is at equilibrium, so that we can calculate the pH. We would do everything like normal. So, you could try the assumption like we've done before. You also want to make sure, again, that you check the assumption, because you might need to go back and sort of solve it a different way. The very last thing I think we talked about was percent ionization. And percent ionization of an acid is basically how much H plus comes off. And for a base, it would be basically how much OH minus comes off. And really the percent ionization formula is the same formula that we use to sort of check our assumption when we do make the assumption. We basically take the amount of free H plus and divide it by the initial concentration of the acid, times it by 100, and that will give you your percent ionization. And again, that's the same way that we do our sort of check in that particular case. Any questions on any of that stuff there we talked about? Okay, so we talked about weak acids, but weak bases also obviously exist. And because there are weak bases, they will mainly stay together. So a reminder that, most bases that have hydroxide in it, especially ones obviously from group 1 and group 2, are a lot of our strong bases. But not all bases will actually have hydroxide in their formula, but they can produce hydroxide in NH3, which is ammonia. This is a weak base. And definition of a base is it's going to accept the H plus. And in this case, it will accept the H plus from the water. That is what's going to really produce our hydroxide here and basically make it a base. We can write an equilibrium expression for this like normal, where we will leave out the water because it is a liquid. And this gets us another K value. This is a KB value, which is the weak base ionization constant. And much like kind of the Ka value that we talked about, the Kb value, as it increases, so does the strength of the weak base. And it's really for the same reason. Once again, when we have a large value for K, that means that we have more products. And as we can see here on our product side is hydroxide. So the larger the Kb value, it means it will actually be producing more free OH minus, making it a stronger weak base. Again, much like the acid, it is obviously a lot less weak or a lot less strong than a stronger base. I butchered that whole saying there. Let me try that again. So just like the weak acid, a weak base, even though it may be a strong weak base, is still weaker than a strong base would be, obviously. A couple of things. We basically will do an ice table for weak base problems the exact same way as we do weak acid problems. The difference here is we will be solving for X, and in this case, X will equal the hydroxide concentration. So typically in these problems, you'll get that X, which will equal the OH minus. You then need to go to the POH, and then you need to go to the pH. So a couple of extra steps that you sometimes need to do here with our weak base type problems. But basically everything else works the same. You can make an assumption if it works and all those things. I will say that unlike weak acids, where we oftentimes will perhaps not put water in the equation, a lot of times it's a good idea to put water in the equation for a weak base so you can kind of visually see it. People really struggle with the base sort of equations. And so a lot of times we will oftentimes include the water in there. Okay. So here's some tables from your book. Obviously, it's some weak bases and their Kb values. A lot of organic guys are weak bases. So why don't we give one a go here? An amine compound has a bad smell. The Kb of it there is 5.6 times 10 to the minus 4. What would be the pH of a 0.15 molar solution? So take a few minutes to see what you come up with here. Okay, let's take a look and see. So first off, a couple things. Obviously, we have a Kb value, so that tells us we're dealing with a weak base. And obviously, much like our weak acids and Ka values, Kb values would be only for weak bases. So strong bases, again, would not have a Kb value associated with them. Again, because they are basically a one-way street, they're going to 100% break apart a strong base. So only a weak base will have a Kb value. So we want our equation here because we're going to need to do a little ice table action, I'm thinking. So C2H5 NH2. Once again, I would recommend using water in the equation here. And just remember that it is a base, so it should be accepting the H plus coming over. that point, we're just going to add our H plus in there. So C2H5 NH3 plus and our OH minus here. And once again, that is why it is a base. At this point, we're going to do our ice table. So initially here, we got 0.15 and 0 and 0. Change here will be minus X plus X plus X. And that means at equilibrium, 0.15 minus X, X, and X in this case. Why am I not putting anything with water? It's not really part of the equilibrium, right? So best not to put any numbers where you might want to use it incorrectly. At this point, this is going to go into our KB expression, right? And that in this case would be our C2H5 NH3 plus OH minus divided by C NH2. And that means that gives us basically X squared divided by 0.15 minus X is equal to 5.6 times 10 to the minus 4. Any questions on the ice table or anything up here? At this point, we do have a small value for our KB, and we can assume X is equal to 0, which would just like before, it would be this X we would get rid of. And just like before, you should have hopefully checked and saw it was a 6.1%, not such a good deal. All right, so slightly over what we accept at 5%. So we do need to solve this the other way here. So I'm going to do that on the next page here, I think. So I'm going to come back to my X squared over 0.15 minus X is equal to 5.6 times 10 to the minus 4. Again, here we're going to basically take this to the other side, right? And when we do that, gets me X squared is equal to 0.000084 minus 5.6 times 10 to the minus 4x. Bringing everybody to the same side gives me something like X squared plus 5.6 times 10 to the minus 4x minus 0.000084 equals 0, right? That's going to be our A, B, and C action here. So we're going to go with our quadratic, which would be minus B, which would be minus 5.6 times 10 to the minus 4 plus or minus. Once again, if you kind of do all the numbers inside the square root before taking the square root, I think you end up with something like 0.003363. Once you square root it, I think you end up with 0.01834. All going to be divided by 2 times A, which in this case would be 2. Going to give us 2 X's in this case, going the positive root there first. Will get us X is equal to 0.00889. Going in the negative direction, which probably is not going to be good, minus 0.00945. Questions up to there. At this point, obviously, we can take a look back at our table here. And really, we had X, I think, and X, if I'm not mistaken, and 0.15 minus X. So clearly, we can have a negative number, so that's not going to work very well. In this case, our X was basically the hydroxide concentration, which means that this is equal to the hydroxide concentration. That's going to allow us to calculate not the pH, but the pOH here, minus the log of 0.00889. Going to give us a pOH of call it 2.05. And obviously subtracting our 14 there will get us over to our pH of 1195. Yeah. Question on that calculation. Yeah. I say again, I did not use the assumption here because technically it was 6.1%, which is over our 5% rule. In this case, it's very, very close. I think you get 11.96 if you did the assumption. Won't always be that way, but in this case, we didn't use the assumption because it was actually 6.1% when you checked it. Yeah. Couple other things to remind you. Again, a good reminder that you should check your assumption. The other thing is you should really make sure things make sense. Sometimes people get to hear and think that is my pH, and obviously that would not make sense in this case. This is a base, right? So this one does make sense because that is obviously a basic pH. So sometimes people get done with the ice table and realize, I think that's the pH, when it's really the POH. Question on weak base type problems, pretty identical to weak acid problems, except POH and then to the pH. All right, so let's talk about sort of an important relationship between Ka and Kb. And if we take a weak acid sort of equation with a Ka value like we have at the top there, and we add it to basically a weak base reaction like we have on the bottom with a Kb, we basically will make water. So we basically will make water, which is Kw. So when we add these equations together, what do we do with the K values? We do multiply it, yes. Hopefully you did that, yes. So we do multiply it here. And that means we get a really good relationship of, if you take the Ka value times the Kb value, it will equal Kw, and that Kw is the same Kw we used before, which is R1 times 10 to the minus 14. So again, it's the same thing there. So basically, we take 1 times 10 to the minus 14 divided by the Ka, it'll get you Kb, and vice versa. Now you may be asking, why would you want to do that? Couple reasons. One, you may need a Kb value and you're given a Ka value. And that's a very common type of situation that occurs during hydrolysis problems. They kind of give you the wrong K value in a sense. They'll give you the Ka when you really need the Kb, and vice versa. You may not be able to maybe find a Ka value or Kb value in the table, but you can find the other, so you could switch it out and stuff like that. So these are good things to remember and a good way to switch between Ka and Kb. So let's talk a little bit here, though, about acid strength. And in terms of acid strength, it does sort of depend on the type of acid we're dealing with. There's kind of two types of acid. This is an acid that basically does not contain oxygen. So this is a lot of your group 7s, your HF, your HCl, your HBr, your HI. And you may think that what would be the overwhelmingly thing that we would look at is electronegativity. But actually, in this case, it's actually not electronegativity that we look at. It's actually bond strength. And we look at the bond strength, and that helps us determine sort of the strength of an acid versus another. Bond strength, right, or bond enthalpy is sometimes referred to, or bond dissociation energy, however you want to word it. That is the energy required, right, to break or make basically the bonds. You might have did some of that when you talked about Lewis structures and bonding. You add up all the ones you broke, you add up all the ones you made, you add them together, it gives you the delta H or the reaction. So if we look at going down sort of group 7 there, our HF bond is 568 kilojoules of energy. Our HCl is 431 and down to 298. So what we see here is the actual strongest bond is the HF bond. And that actually will make HF a weak acid. Why would the stronger energy make it a weaker acid? What is the definition of an acid? Something that's able to do what? Something that's able to produce H+, right? So in order for this guy to produce H plus, you gotta break that, right? Set it free to produce H plus, which means if it takes a lot less energy to do that, the H plus is gonna come off a lot easier, and it would make it a much stronger acid than, say, HF at the top there, which takes a lot more energy to break that bond, which means it's not going to give away its H that easy, and thus not produce a lot of H plus and make it a weaker acid. So when we have no oxygen in the acid, we really look at bond energy as the overwhelming sort of thing of which one should be stronger or weaker. And as the bond energy increases, the strength of the acid decreases, it goes down. So in terms of the order here in strength, it actually increases in strength as you go down group 7. That's why HI and HBr are strong acids, HCl is a strong acid, and our H up there is a weak acid. Now, when we deal with acids that do contain oxygen, we do have to look at a couple of different things depending on the situation. And here's just another graph from your book that describes that. These are what are sometimes referred to as oxyacids because they contain oxygen, and a lot of times they contain the polyatomic ions in them as well. Now, when we look at a oxyacid, it typically has this bond happening here somewhere. This OH bond, that's polar, non-polar. That is a polar bond, yes. The oxygen being more electronegative, kind of going that direction. That means already, right, the electrons are pulling towards the oxygen. That's going to help weaken that bond a little bit, and that's really the hydrogen that pops off when these guys really release their hydrogen, is off of that kind of OH connection there. Now, we look at one of two things. In certain cases, we look at the electronegativity. Electronegativity, right, is the ability of an atom to bring electrons towards itself. Increases which way on the periodic table? Up and to the right, yes, it increases. Decreases down. Most of the electronegative element is thought I heard somebody whisper fluorine. That would be right if I heard a whisper. I was really trying to hear it. In other cases, we will also look at the oxidation state or oxidation number of a particular element to help us decide, you know, which one is sort of a stronger acid or a weaker acid. So let's look at both of these situations and when we kind of would use one situation maybe over the other. So in a situation like this, where we have an oxyacid that has a different central atom that are from the same group, but have the same oxidation number, the acid strength actually increases with electronegativity. Let us review oxidation numbers or states really quickly. We'll talk about it in a later chapter as well. Oxygen is usually an oxidation state of -2, which is a good place to start. That would be -2. That would be -2. Hydrogen is +1. When we add up all the oxidation states, it needs to equal the charge on the molecule. In this case, there is no charge, so they need to equal 0. Which means that's a -2, -2, -2, that's a -6, and a +1 is a -5. That means that the chlorine here is actually +5 in this arrangement. Same thing over here, that's a -2, -2, -2, and a +1. Once again, adding that all together gives us the bromine that is +5. Now, a reminder that, and again, we'll talk about it a little bit later on as well. You might have talked about this when we talked about redox reactions, maybe. But the oxidation state or oxidation number is not really necessarily the charge that we assume that the element has, like in an ionic compound. In an ionic compound, electrons are fully what? Transferred, right? So electrons are fully transferred from one to the next. So the elements gain certain charges, like chlorine gains a -1 charge and bromine gains a -1 charge. This type of bonding here is not ionic, right? This is what type of bonding? covalent bonding, which means you're sharing electrons. So in this arrangement, the electrons are not being transferred, but they're being shared. And the oxidation state is basically the charge that that element takes through the sharing process with all the elements that are present with it. So in this particular case, the chlorine and the bromine both are taken on a more +5 sort of charge rather than the normal -1 that you associate in an ionic compound. Any questions on that there? So really in this case, we have different central atom, but everything on the outside is the same. When we have this situation, we're going to look at electronegativity. And once again, as we talked about, electronegativity does increase as you go up in a group. And that in here would be more electronegative. So why is that important? Well, if we look at this, we have the oxygen being more electronegative, which means the electrons are heading towards the oxygen to begin with. That is weakening this bond. Now you got the chlorine here that's also more electronegative, which is going to pull those electrons even further in towards the chlorine, which is going to weaken this bond a lot more and allow it to come off easier than bromine that's not going to pull the electrons as much. You're going to make it harder for it to come off. So in this particular case, it would be our chloric acid here that would be a stronger acid than the HBrO3. So if you got the same oxidation state on that central atom, you want to look at electronegativity. The one with the higher electronegativity would be the stronger acid because it's going to allow the H plus basically to pop off a lot easier. Any questions on that there? Now let's take a look at sort of the opposite situation. If we have an oxyacid where the central atom is basically the same element, but has different oxidation numbers, then we actually look at the oxidation numbers. That's because the central atom here would obviously have the same electronegativity in all of them, so that wouldn't be helpful. In this case here, if we leave the little oxidation numbers, oxygen always a good place to start. That's -2. Hydrogen is +1. In this case, it equals 0. So the chlorine is +1 in this case. Over here, that is -2 for the oxygen, -2 for the oxygen, +1 for the hydrogen. That is -4 and +1 is -3. The chlorine here taking on a +3 persona there. This is the one we just did, -2, -2, -2, and +1, giving us our +5. And now perchloric acid, -2, -2, -2, -2, and +1. That's a -8, and a +1 is a -7, which means to balance it out here, our chlorine is taking a +7 oxidation state in this particular case. The strength of the acid increases with the oxidation number for kind of the same reason. You got that OH bond, and then you got this really big positive charge here. So as the electrons move this way, they're going to be more attracted to that higher positive charge in the center. All that's going to weaken that bond a lot easier and allow the H plus to come off. So in this case, this would be our strongest acid, next, and last in terms of the order. Any questions on that there? Yeah. It is in a case of a oxyacid where you have oxygen and the central atom has the same oxidation number. Because obviously if they have the same oxidation number, you can't look at that because they're basically equal. So in that case, you would look at electronegativity. Here in this example, we have oxygen or oxyacids where they have the same central atom, which means that central atom has the same electronegativity in all cases. So you can't look at electronegativity here. You have to look at the oxidation number. Other questions? Yeah. So the next thing we're going to talk about is actually salts, and just a reminder of where salts come from. When I take an acid plus a base, the two things I make are a salt and water, right? So like if you take HCl plus a little sodium hydroxide action. Basically, what's going to happen is these two guys are going to switch partners, and we make water here and a salt, which would be sodium chloride in this case. So salts are really derived from sort of the product of a reaction of an acid and base. And it's really important to remember that, because a lot of times when you're dealing with salts, it's really important to think about where it came from, and sort of where it came from, what acid, what base it came from. And that oftentimes can help you understand how to kind of do the math part. The other really important thing here is the relationship that we talked about earlier on between these things, like a acid and its conjugate base, or even a base and its conjugate acid. So the relationship I'm speaking of is, if my acid is strong, the conjugate base will be strong or weak. It will be weak, right? It's an opposite relationship. If my acid is weak, my conjugate base will be relatively strong. So that relationship that we talked about earlier is really important here when we're talking about salts. And the same thing, obviously, for our base. If we have a strong base, a relatively weak conjugate acid. And if we have a weak base, a relatively strong conjugate acid in this particular case. Why is this important? It is important because in certain cases, if you produce a salt and it's relatively strong speaking, it will decide it would like to continue to react. And who is it going to react with? It's going to pretty much react with water, is the only thing there. And it will continue to actually react with the water that's present. The effect of the salt and the water reacting, if it does, is it will do one of two things. The salt will react with the water, and the salt will act as a base, and it will accept an H plus from the water, and it will produce basically hydroxide. The other option would be the salt kind of acts as an acid and actually will give away an H plus, and that will produce H3O plus. So if we come across a salt that is considered strong, and by the way, the strongness there is not like a strong acid or strong base, but relatively strong in the sense that it will continue to react with water. It could continue to react with water and produce hydroxide or produce H3O plus. And why would that be important, either one of these reactions? What would it do to our solution? When you make OH minus, what type of solution are you probably dealing with? You are dealing with a base, yeah? So you're going to probably have a basic solution in this case. And when you make H3O plus, it is a acid, yeah? So the consequence of a salt continuing to react with water is it will actually make the pH of that solution either acidic or basic, or if it doesn't react, it will just be like neutral, but it will make acidic or basic in the other direction. By the way, we talked also about the idea of Ka's, right, values, and Kb values, right? How do I know which one I should use in which place? Like if I wanted to use a Ka value and I look at my reaction, what should I see? What should I be looking for to know I should be using a Ka value? What should be in the equation? In the equation should be like H3O plus, yes, or H plus, and it should be on which side? Should be on the product side. So if you write an equation or a reaction and you produce H3O plus on the product side and you need to do a calculation, you should be using the Ka value. If you are going to use a Kb value, you will see hydroxide on the product side. So if you write a reaction in an equation and you get hydroxide on the product side and you need to do a calculation, you should be using your Kb value. And this is why it's really important to be able to write these equations correctly so that you use the right value here. This is also, as I mentioned a second ago, where the Ka times Kb equals Kw comes into play a lot, because these are historically the problems where they will give you the wrong K value. You actually need the other one. So being able to write the equations properly and understanding that if you see hydroxide on the product side, that's like a base situation, Kb should be used, or you see H3O plus on the product side, that is a Ka situation or an acid situation. We'll go very long in doing these things correctly. So let's talk a little bit about neutral solutions and neutral salts. So for example, there are certain salts that are basically what are considered neutral salts, which means that the pH of the solution would be a 7, which is neutral. So those are salts that contain alkali metals or alkaline earth metals. That is group 1 and group 2 on the periodic table. That is because group 1 and group 2 on the periodic table are pretty much where what type of bases come from. Those are typically strong bases, right? So if they're strong bases, the salt part of it would be relatively weak. So because group 1 and group 2 are things where you find sodium hydroxide, potassium hydroxide, calcium hydroxide, and so forth, anything that comes from there is going to be relatively weak and basically be a neutral salt. Anything that comes from basically a strong acid or a strong base is going to yield you a salt that's going to be neutral because they're both going to be weak. And we saw that on the previous page here where I wrote this equation right here. That is a strong acid. That is a strong base. And the salt we made is something that came from a strong acid and a strong base. When we look at the sodium chloride, it is basically two things, sodium ions and chloride ions. That is group 1, which means it comes from a strong base, neutral, not going to affect the pH of the solution. This comes from our HCl, which is a strong acid, which means this is also going to be relatively weak in terms of our hydrolysis conversation. So both parts of the salt, both ions of the salt are going to be basically neutral. And if you had to get the pH of that solution, it would be a pH of 7. It should be a neutral solution in that case. So anything that comes from a strong, the salt should yield a neutral salt, and you should yield a pH of 7. Now, there are some solutions, or salts, that will be basic. So let's take a look at one. Let's take a look at sodium acetate. So that is sodium acetate, which basically breaks apart into two things here. Breaks apart into a sodium ion and an acetate ion. So when you have a salt, this is pretty much what you want to evaluate. You want to evaluate both of the ions that are present in the salt. And you want to determine, will either one of them, or will both of them, or will neither of them go through hydrolysis basically and react with water. So to help you do that, it's really important to think about one step back of where the salt came from. So if you had to put on your chemistry hats here and take a wild guess as to what acid and base combination here would produce this, what would it be? What would be the acid that this most likely came from? What acid would acetate most likely come from? It would be acetic acid, yeah. So this most likely came from the reaction of acetic acid and what base? NaOH, yeah, probably sodium hydroxide. So this is probably a reaction of acetic acid and sodium hydroxide. And again, it gets a double displacement and you get water and your sodium acetate that's basically occurring. Basically, this guy and this guy are switching partners. Now, knowing that it most likely came from acetic acid and sodium hydroxide, we want to think about each of those acids and base. Is acetic acid a strong or weak acid? It is a weak acid, and if you don't know that, you will by the time we're done in the next several weeks, because it just pops up everywhere, like all over the place, acetic acid. So acetic acid is a weak acid. Sodium hydroxide is a strong base, right? So now we have sort of our relationships here. So we know obviously the sodium ion came from the sodium hydroxide, and sodium hydroxide is strong, which means the sodium is going to be strong or weak. It is going to be opposite, which means it's going to be weak. So that is like the neutral salt that we just talked about a second ago. The acetic acid is where the acetate came from. So the acetic acid is weak, which means the acetate here is going to be relatively strong, right? And in this concept here, it's basically going to be strong enough to continue to react with water. So what's going to happen when we have this salt is it's actually just going to be the acetate part that is going to react with water in a process known as a hydrolysis reaction. The other thing that people have a really hard time sort of figuring out is what happens when it reacts with water. So knowing where it came from can also help you. Because it came from acetic acid, which is a weak acid, that means technically speaking, our acetate is the conjugate base. Yeah, so if it comes from the acid, that's its conjugate base. And that's important because when it reacts with water, it's going to react as a base. And a base does what? Accepts an H plus. So it's going to accept the H plus in this case, and it will make a little acetic acid here. And it will make some hydroxide in this particular case. And in this particular case, we make exactly where it comes from, which by the way, always happens. So in case you need the equation, it always makes where it came from. So that's why it's good to know where it came from. And more importantly, without even doing a single calculation or picking up our calculator, it is producing hydroxide, which means the solution should be acidic, basic, or neutral. Should be basic because we are generating hydroxide. Also means that if we did want to do the calculation, what K should I use? KB, yeah. So again, really important to be able to write these equations or reactions. It will help you go down the right path in terms of the calculation part. So any salt that basically comes from a weak acid will produce or will be produced a salt that is relatively strong and will go through hydrolysis. It will always go through hydrolysis as a base, and that means it will always produce hydroxide, and you will always get a basic solution at that point. Any questions on that there? And that's what we see here. Again, our salt, I feel like it's got an extra H there. And again, it's going to, in this case, accept the H plus, producing that hydroxide. And once again, we do know that this solution should definitely be basic. Now, we could actually do a calculation to figure out the pH of this solution by doing an ice table here. So we would do an ice table in this case. We would solve for X. And X would equal the hydroxide concentration. That will allow you to get to the pOH and then to the pH. So we could actually get the actual pH value here by, again, doing an ice table. Once again, you will probably have the wrong K value given to you, so you'll need to do a little Ka, Kb equals Kw situation here to make sure you are using the correct K value, which is probably 99% of the time where people screw up. They use the wrong K value and stuff like that on these things. Now, we could also have a salt that is an acidic salt. And let's say we took something like ammonium chloride, which I think is what you have on your paper there. So ammonium chloride is a salt. And once again, it breaks apart into ammonium and chloride. So once again, if we're not sure what's going on or where it came from, if we had to make a good educated guess here, this is probably the reaction of NH3, which is our weak base, plus a little hydrochloric acid. And that would be how you would produce NH4 plus and Cl minus. Or if you want to put them together, ammonium chloride, just stick them together. This is a weak base. This is a strong acid. So now when we look at our parts here, we want to analyze, will anything go through hydrolysis? Will the NH4 plus, which is related to this guy, will he go through hydrolysis? Is he going to be relatively weak or strong? He is going to be strong, which means he will go through hydrolysis because it comes from a weak base. What about the Cl minus? Will it go through hydrolysis? It will not, because it comes from a strong acid, which means it's going to be relatively weak. No hydrolysis happening. It's basically a neutral salt. That means in this particular case, it's the NH4 plus that's actually going to continue on to react with water. And that would be our reaction here. We would take our NH4 plus, react it with some water. And once again, because it comes from a weak base, the NH4 plus would be its conjugate acid, which means it's going to act as an acid over here. And the definition of an acid is it's going to donate, in this case, an H plus over to the water. When it donates the H plus over to the water, we get NH3, which is where it came from. Again, you always get where it comes from in this reaction. And you will produce H3O plus. So once again, at this point, because we are producing H3O plus, we should know that this solution should be acidic because we're producing that H3O plus. We also know that if we want to do a calculation here, we should be using a Ka value in this case. And once again, if we were to do that calculation, it is going to be a nice table here, where in this particular case, when we do solve for X, that will actually equal the H3O plus, which means you could go right into the pH at that point and get the pH. Any questions on that there? So any salt that's basically derived from a weak base will go through hydrolysis, and it will go through hydrolysis basically as an acid, and it will always generate H3O plus. And again, you would expect the solution to be acidic. Any questions on that there? Again, that is what we see there. Producing H plus, going to be. Now, there's also another way that you can kind of produce an acidic salt, and it comes from small, highly charged metals like +3s, +2s. A lot of times transition metals do this a lot. But when we have some metal that's floating around in solution, it's really surrounded by water, which is what the aqueous means. So that is basically what this is here. So if we take a look at this guy, here, I think. So we had AlH2O6, I think, 3+, right? So basically, this is the same as this. Basically, aluminum floating around in the solution, basically. because water is polar, right? It's going to go surround that ion that's floating around, right? And that's basically what it is as it's floating around. The guy on top is sort of the expanded formula for aqueous. So basically what we have in this situation is we have this aluminum in the middle. We got 6 waters in this case. I'll just draw out one. And what's going to happen in this particular case is, because this is a relatively small but very positive sort of center, we're going to get kind of the same situation we talked about with acid strength. We have this bond here, which is polar, right? So their electrons are kind of heading in. And then we got this nice positive charge in the center, which is going to bring the electrons in a little bit more. That's going to weaken this bond pretty good. And what's going to happen in this situation is just a regular water, just a plain H2O is going to roll through. And it's basically going to take that H off of that guy. And when it does, that is basically how we would produce our H3O plus, which is known again as the hydronium ion. Yeah. And the result of that is, when this reaction is done, out of our original sort of metal, the only thing we took off was an H. We have 1, 2, 3, 4, 5 intact waters. And we have an OH, right? And plus 2 left over. So basically when this guy goes away, it becomes OH. And that's how we get to that formula that we saw on the previous page here. Basically 5 waters, an OH, and the charge changes as well. But the main thing here is we're able to produce some free H3O plus, which means that we would expect the solution basically to be acidic. Any questions on that there? So 3 different types of salt. One is a neutral salt, pH is 7. One could produce hydroxide, which is considered a basic salt, and that comes from a weak acid. And one that is considered an acidic salt that can produce H3O plus, that comes really from a weak base. So again, it's really important in this chapter here to think about things, where they come from and how they work. So for example, why don't you take a second here, what would be the pH of a 0.45 molar KCl solution? Okay, so let's take a look. So we got a salt here, which is potassium chloride. So we got this guy, which would break apart into K plus and Cl minus. For the most part, most salts are strong electrolytes, which means they should kind of completely break apart. So the question here is, will either of these guys go through hydrolysis? So once again, we could kind of look at the salt and think about perhaps where it might have came from. What acid maybe would have worked here? HCl, yeah. And a little potassium hydroxide is probably the acid-base combination that produced this. The H would come over here, the K would come over here, and we would produce water and KCl, right? So that is most likely the acid-base combination there that kind of produced this guy. That means that this acid, which is hydrochloric acid, is strong or weak? It is a strong acid. And KOH is a strong base, yeah. So that means that really our Cl part came from HCl, which is strong, which means, will the Cl minus go through hydrolysis in this case? It will not. It's a neutral salt because it's relatively weak. And really our K, which is group 1 or 2, because it comes from a strong base, will also not go through hydrolysis. So the pH here should actually be 7. It should be neutral in this case. No real calculation is necessary. Any questions on that there? So let's take a look at one where maybe we do need to do a calculation. And this one, you do need to do a calculation. So why don't you give it a try here? What is the pH of this solution? That is 0.3 molar sodium fluoride. The Ka value of hydrofluoric acid is 7.2 times 10 to the 4. And so let's take a look at this. We have sodium fluoride, which would break apart into Na plus and F minus. So the thought here is, will any of these guys kind of go through hydrolysis? The answer is yes. And which one would go through hydrolysis here? If you're not sure, there's a lot of information that is sometimes given to you in the problem that you should not just overlook. So let's take a look at sort of what else is in this problem, what we got going on. Maybe we got something going on. We got a Ka value that's given to us, right? Ka value is for HF, which is hydrofluoric acid. That would imply that HF is what type of acid? Is a weak acid, right? And most likely the F minus came from HF. So that tells us automatically, I'm sure that we're going to have some hydrolysis happening here. And it's going to be really the F minus that's going to go through it because it's right there. The nice thing about that as well is it will also help you with the reaction that should take place. By the way, the sodium will not, right? Because it's group 1, so it will not go through hydrolysis. So we're really just looking at this guy. And we would always have this reaction sort of occurring. Now, because this obviously is an acid, our F minus will act as its conjugate base, right? And that means it's going to accept the H plus over here. By the way, logic also tells us that F minus doesn't have an H to give, so it cannot give it, right? It can only accept it in this case. When it does, it is always, like I said, going to make where it came from, which means in the actual problem, you actually have that there for you. And this will then produce hydroxide. Once again, without even doing the calculation here, we should end up with a pH that is basic. Yeah, so we know just from the reaction here and the equation that we should end up with a basic pH. We are going to do an ice table here, and we will do it next time. But why don't you finish it up and we'll see how everybody did here next time. Any questions on anything we talked about here today?